Okay, thanks. Welcome back, Shabab, to the class. I would like to announce that I already posted the slides for this chapter until section 11.6. So, as I promised, I will keep updating these regularly. And just to show you that last time I missed the point when I said, oh, I did not add your some sort of a catalog examples. So this is a slide. If you look at it carefully over here, you will see that this is, just to go over it very quickly, see that this is the bore size, okay? This is the OD of the bearing. This is the width, the fillet of the radius. This is the shoulder. These things are very important, the shoulder, the fillet. When the bearings sit on the shaft, you want to make sure that these one match the, you know, the same sizes on the shaft. And then we have this deep groove C10. Remember what is C10? Is the rated 10 percentile life. And we have a C0 here over there. So what is that C0? This actually table belongs to a section which is not supposed to be covered in here, but I'm just showing it to you. We will talk about C0 later. This one is the angular contact bearing. And again, it has a C10 and a C0. Good. So the C10 is the rated 10 percentile life. And the C0 is another rating, which we are going to discuss later. So also, I remember Suhail, was it? Suhail?
Yes.
Yes, you're the one who mentioned this. And I went home and I calculated it. It seems like all the calculation here are right, but the conversion is wrong. Okay. So I did the conversion and it seems like it is 14.3. I am not very surprised, ya shabab, don't worry, but I am not very surprised because this book was going through hell. I mean, they wanted to introduce an SI unit version, and then they want to introduce one which is mixed, and there are standards that were developed in pound, and you can hardly change them. So this conversion is going crazy, and I'm not surprised that there is a mistake on it. So it's not 16.4, it's 14.3, just for you to know about this. Now, where did we stop last time? In the normal distribution. Yeah, I told you I'm going to talk about the normal distribution for a little bit, and then hopefully this sets the ground for you to understand the Weibull distribution. So the known Gaussian, which is famously known as the normal distribution, has a probability density function, which is BDF, a probability density function, which is expressed based on two terms. The first one is the mean, and the second one is the standard deviation. The first one, which is the mean, is probably the most loved statistical parameter by all students. And because it's the average that you all love. And you don't probably like to talk about the standard deviation, which gives you a measure of how far, if we want to talk about it, how far each grade is supposed to be from the other. And this is where you get so angry, right? So you want a mu x, which is the average, just like giving it a little fancy mathematical name, mu x, yeah? How much do you want it, ya shabab? B plus. Hopefully my kids, which are like tiny and little right now, when they join KFUBM later, the average will be a plus. How about that? So, and then no student will complain. Now, because especially I asked many professors, and they said, what's going on? Is it our student only? God, you will hate me. But all of our students want the average to be B plus or B. Yeah, B plus, something like that. So why I'm talking about the average and you know, without trying to upset you, is because naturally grades are of a normal distribution. If you have a class and then you give a quiz to the same student, not online, of course, where people might cheat, you expect in general that there are students who will crumble within, oh, you know what, leave this example. Wait a second. If you have a normal distribution, which is famous, this famous hump curve, uh, squeeze this way. What does that mean? It means that all of you are here. There are only maybe one student who get an A, and maybe, God forbid, nobody got an F. Maybe one student got a D, but all of you got a B. Maybe. Or all of you got a C. So you don't want that. What you want is this. You want a reasonably flattened normal distribution where some of the majority got C's and C plus and maybe B. But there are also, unfortunately, students who got a D and C and D plus. And there are, of course, the winners, the A pluses. Now, unfortunately, the only way to drop this down sometimes is by having more people here. And unfortunately, this makes you so evil, right? Trying, to wish for too many to get a D. That will flatten the curve, sadly. So let's not talk about emotions over here. In general, if we give that quiz to the student, in general, we believe that what we are going to get is a normal distribution. So I promise you, we are going to do this exercise for our course. Each time I'll do my best, spend time, and show you the distribution of the grade. It goes the same with your height. If we take now, we have 33 students. If we take, actually less, 31. If we have here the population and we ask them, what is your height? But, less sensitive than the weight. And then we can expect in some sense that people in general will be around some number. And there are people who are a little bit toward the short side, and there are people who are a little bit toward the high, height. That's the story. Halas, I think this is good. Now, what is the probability density function? It is fx. X here is the dimensionless life measure. If you recall, we said that X equals to L over L10. L10 is the rated life. L is the life of the expected life of a certain variable, right? Now, if you look at the equation, it has mu and sigma x hat, and that's it. The X is the life dimensionless measure. And as we said, the normal distribution will need two values, the mean and the standard deviation. Now, what happened next is this. The probability of a student to get an A, to get an B, if you look at the distribution, is basically the area under the probability density curve. And of course, nobody likes to do integration, at least the majority of people, because the area is the integral. And so what do? The statistician, that's the work of statistician. They said, okay, let's transform that equation. Here, we take this part and we call it Z. And then we transform the integration. And by transforming it, we make it into a simpler, computationally easier function. And then we have, instead of fx, we have fz. And what do we have? We will have the probability as here. Yeah, so that's data. So you give me a number, and I tell you what is the probability that that number will come about. Like a bearing based on certain distribution, what are the chances that that bearing will get this life or the other? So
Doctor,
they, yes?
sigma x is to the standard deviation.
It's the standard deviation, sigma x hat, yes. And mu x is the mean, the average, okay? Now, in simple, we don't want to spend time on this, ya shabab. In simple, or in short, I mean, if you go to a table A10 back in the book, you will see the integration of the normal distribution. So I just need to warn you about one thing. If you end up with minus, for example, 1.1, you want to know what is the probability. Then you should know that this table was tabulated, was made for a negative value. So if you have minus 1.1, what are you going to do? You will go to this. This is 1.1, which is minus. So if you have 1.100, then this is 00, and you will get this probability. If you have minus 1.11, then this is a 0.01 added to 1.1, and you will get this number. That's it. Okay, we'll have example. Don't worry about it. So, what is this has to do with bearings? Well, bearings are like everything else. If you look at their failure rate, it turns out that they do not follow a normal distribution. Now, interestingly, ya shabab, if you read in the literature, even in the internet, they will tell that Weibull distribution is actually very, I'm not going to say very accurate. It's actually representative of many failures. That's it. Somehow failures, Failures. I'm not talking about grades. I'm not talking about weight, height, length, speed, average number of population in a mall. No. Talking about failures. Weibull distribution seems to express them very nicely. And Weibull distribution is actually skewed. And what does this mean? It means to the right. It means that it is not like the normal distribution, which is like this. No, it isn't. It is like this. It is not normal. Now, as you know, from a geometrical point of view, just look at it as a geometry. It is not symmetric, right? It has a little shift. So mathematically, you cannot explain this like the normal distribution with two parameters. So Weibull distribution is in general has 3 coefficients. What you need to do, what you need to understand is the following. We are not statisticians. We are not doing a class. You need statistical analysis when you go to the industry. The famous, what is it? Six Sigma belt, black belt, is a very well-known terminology, certification for, probabilities and so on, and reliability analysis in the industry. But with us, what are we going to do? This is a work of an experiment, or experiments. You cannot expect me to expect you to know these numbers or you derive them. Nobody can. They are a pure experimental observation. So what do we do? Just to make it easy on you, don't you feel nervous? This reliability based on Weibull distribution, R is expressed as this equation, which is the exponential of minus x0 divided by theta minus x0 to the power b. This b, this x0, and this theta, all of them are coefficients. The x0 is the guaranteed value of x. The theta is the characteristic parameter, and beta is the shape parameter that, control the skewness. So these values, you cannot invent them, don't worry. These comes naturally. When you test bearing, they behave that way. So a company must report their Weibull distribution coefficient. These are three. In order for you to use that numbers to make judgment. You understand? And we will see the example. Don't rush. So B is equals to 1.5. In general, we will see what is theta. The theta correspond to 63.2121 percentile of value. Now, one student in the other class asked me a question, not in this slide, on the other slide, about rounding up numbers. And I want to tell you that you have to be very careful. So if we say that the probability of failure is 10%, then what is the reliability, ya shabab? Is 90. Right? When you say that the chances that something is going to fail is 10%, then you are indeed 90% reliable. And don't make it, ya shabab, like a joke. One day you go to the industry and tell you, how much reliable are you? 100%. And then you tell them, what are the probability of failure? Well, as per the manufacturer, it's 10%. They're gonna laugh at you. You don't do that, ya shabab. No. The reliability is 1 minus the probability of failure. It's just, you're looking at the bad side, which is the probability of failure, or the good side. So if you want to be a good marketer, you want to sell bearings, you're probably going to talk about reliability. You're not going to talk about the probability of failure, unless the client asks you so. So the distribution, the probability density function of the Weibull distribution is given as this. And now, what do we want? We want, of course, ya shabab, if the distribution is skewed, it means there are more chances of one event to happen over the other. Yani, for example, if we say that for some reason, the class probability was like this. I mean, no, the distribution of the class was like this. Of what? Of the grades. Then you can call me a butcher, Jazzar. Why? Because if this is the F, it's very clear. Well, what is happening right here? This is a crisis. The whole thing is going toward the F. And similarly, don't be happy. Something weird if it is like this, where this is the A pluses, which means that people way more getting, well, what's going on? Either you guys are cheating or there's something wrong. Of course, you need to understand here. I am not talking about the fact that this is a must. This puts a question mark. You may get a chance to be in a class where there are a huge number. I remember one time I had a class. I had like maybe 8 or 10 students, which are true A pluses. I mean, even if my curve turns out to be like this, I don't care. I will never force them to fail. But I'm telling you, I'm talking about a question given to a student, And by the end of the exam, okay, or the quiz, you ask a student and they tell you it's fair. Come on, you guys say things are fair. You don't always say it is difficult. You don't always say it is easy, right? And then the grades turns out to be skewed. This is where the question comes. You understand? So what are the expectations? Is that the mean and the standard deviation is different. Sure. How, ya shabab? If they are skewed toward that side, the average is not going to be just add the grade of the student and divided by the number of students. That only applies for a normal distribution. That's why I want you to appreciate and never make the mistake by knowing that if you have a distribution which is other than the normal distribution, your basic understanding of the average as the sum divided by the total is wrong. It doesn't make sense. You should know, you should say it is not that, even though I don't know the equation, right? So what is it? It's a mu x, which is equal to this. Now, look here. This is the gamma function. Now, you thought you can run away in mathematics, but unfortunately, you cannot. Now, I bet that some of you have taken Math 333. Is it, ya shabab?
Taking it in this
Is
semester.
it? Oh, you're taking it this semester. They will teach you about the gamma function. And of course, if you have taken the course earlier, you will think that this is useless, insignificant mathematics, which is why they just try to make our life difficult. But surprisingly, this gamma function, the error function, they pop up out of nowhere. Yeah, just to rescue. Or what? Make your life a little bit more difficult. Don't worry. The gamma function, I'm not going to show it to you because if I show it to you, you will be scared and maybe some of you will cry. Is that right? But it's much easier than what you think. I mean, we are not doing a math for, class for mathematics over here. The gamma function, okay, is integrated and tabulated. So all what you need to do is to go. Do you remember that we told you that B is in general 1.5, for example? So if you substitute here 1.5, you go and then you find the corresponding value. So if gamma function of 1.5, for example, how much is it? You go here and say, where is 1.5? Over there. So the gamma function is this. That's it. Now, what you need to do is that to understand that in the example that we are going to discuss, there is an example which involves, calculation of the average, which is the mean, and this one is the standard deviation. And the standard deviation is also involving the gamma function. Now, we'll see in the solution that you cannot just round up numbers. That's not nice. You need to be very careful. I mean, the language of statistics, whenever you have it, you will be surprised. Maybe you will not, but you need to be very careful that all of a sudden, once you are in distributions and numbers, things start to become a little bit weird in the sense that here we have given you this 63.2121. Yeah. And not only this, if you want my advice, whenever you have an equation with an exponent b, x, c, never try to round up that number. If you are given that number in 4 significant digits, just put it as is. Because these guys can blow your number so easy. So easy. So be careful. Now, since this idea that, if you go to statistics, they will teach you that there's definitely multiple ways of looking at things. Like, for example, if you use MATLAB today to fit an equation, you will be overwhelmed. There are R square, there is adjusted R square, there is RMS square, and then so on and so on. What are these? These are some mathematical, well-driven representations of what is supposed to measure certain mathematical or statistical quality or phenomenon. Now, one of these is called the coefficient of variation. It's a very well-standard, well-known statistical measure. It happens that we don't use it often. We just, in a normal standard day, we use the standard deviation. But the coefficient of variation is another measure of dispersion. What does dispersion mean? It means, again, it's the same story. Same story. If you have bearings, ya shabab, okay, and this is bearing number 1, 2, 3, and 4, and 5, and then this is the life, and let's assume this life is in hours, and then you got a life of 2000, then a life of 1990, then 2050, and 1890, and maybe 2100 something. And then you have another bearing where you got 5,900, sorry, it's a 900, not 9,000, okay, and maybe 1,500, 2,000, and then 3,000. If I tell you quickly, you are in the industry, you need to make a judgment, and you have this, and you have this. If I tell you, in average, in this condition, how much life are we expecting? 2,000. You don't need to think about it. Just say it. 2,000. I made those numbers randomly. I didn't make a backup calculation, but when I throw numbers like that, I would say 2,000. But what are you going to say here? What? So the coefficient of variance or variation is going to measure the dispersion for you. It's another measure, different than the standard deviation. And it is equal to the standard deviation divided by the mean. And again, the higher the CV, this is CV. So this is CV for this is high. CV for this is low. The higher the CV, the more you get worried. Why? You know, it may fail at 1,000, may fail at 5,000, I don't know. But here, how much? 2,000. Maybe it fails at 1,900. So at 100, it's not a lot, right? But whenever you have things that are all over the place, it becomes really not easy. So if you now go back and say, for a dimensionless measure of X, which is, again, I remind you, it is L over L10. Okay. What is the reliability? So here we're given a big question. If you look, this is the reliability, okay, and this is what you should expect, right? Of course, if you X is L over L10, and if you know L, you can easily multiply L by X to get L, and you can get the life with a specific reliability. You understand that? So let's look at this example. This example says that we want to construct the distributional properties of a 0 to 30 millimeter deep groove ball bearing if the weighable parameters are x0, which is equals to 0.02, the theta, which is 4.459, and the B, which is 1.483. And this is where the other student asked me, He said, can we just make it 1.5? No. The answer is no. Find the mean, the median, the 10 percentile life, the standard deviation, and the coefficient of variance. You understand that? Now, what is the first thing? Is the mean. The mean is not difficult. It's just we know the equation mu x, which is equal to what? X0 plus theta minus x0 multiplied by the gamma of 1 plus 1 over b. Now, we know that this is given to us, which is 0.02, and we know that this is also given, which is 4.459, and we know that beta is also given, I mean not beta, b, which is 1.483. Now, when you find this, okay, what did you get? You will get 4.033. The question, what does that mean? What does that mean? How can you read it? As an engineer, huh? You're an engineer. You got this number. It wasn't easy. The values, you got them from the manufacturer. The gamma function, you need the table. Maybe smart calculator will do it for you. You got that number. Your boss asked you, okay, what does that mean?
That means, Doctor, the expected life for those bearings will be 4.033.
033. You almost touched the answer. This is x. This is the mu for x. Huh? The average for the dimensionless parameter. So when this is the average for the dimensionless parameter, what does that mean? It means that the average bearing life, the average bearing life is equal to 4.033 what? L10. How? It's like when you have x, which is equal to L over L10, in here, it's like you are measuring the average, right, of x. So if this is the average of x, then L, which is the expected life, is going to be x multiplied by L10. So when you measure the average of x, you multiply it by the rated life, and here you are saying that the average bearing life is 4.033 L10. How? If L10, we said, for most part, I mean, in general, is 1 million. What does it mean to have an average life of 4 millions? 4 millions. Forget about the 333. Just look at this. L10 is 10 to the power 6. Does that make sense? We buy the bearings to survive within 10 percentile a 1 million cycle or revolution. And here you are telling me that the average is 4 million? What does that mean? Well, of course, the average is more than the 10 percentile life. Why? I mean, let's just remember, ya shabab, that the curve is like this.
Because of the Wabble distribution.
And yes, the distribution. Look, ya shabab, the 10 percentile is here, right? But you have a huge number. Let's make it green. All of these bearings, do you know how much would their life is? There is here a chance that when like 20 bearing failed after 2 million cycles. Sorry, let me. Like 2 multiplied by 10 to the power 6. Here, maybe you have 20 other bearings survived up to 4 multiplied by 10 to the power 6. Here, you might get a bearing which can survive 10 million cycles. Who knows? If you add the life of all of the bearings as an approximation, that's not what I told you. The mean here is not the total life of all bearings divided by their number. This is the standard, the average for a normal distribution. But here, in the same sense, there are other bearings that survive way more. So the average, you should not expect that the average is going to be 10. Only 10% failure after 1 million. The remaining 90 survive more in general. You get that? So yes, it will be higher. Now, what about the mean? No, this is the mean. What about the median? The median in statistics, Shahbab, is the measure for 50% reliability. It's different. It's 50% reliability. So what do? We go to this equation and we say x for 0.5, which is 50% reliability, equals to x0, which is known, plus theta, which is known, minus x0, which is also known, multiplied by ln of 1 over 1.5 to the power 1 over b, where b is also known. And if we solve this, what do we get? We get L, which is equal to 3.487 L10. This one is telling you that the chances of survival for bearings, the number of bearings that will survive in another way. No. I want to tell you this. The idea here is this. The bearings that will end up surviving, okay, with 50% chance is 3,487,000 something out of, if we consider that L10 is 1 million.
Doctor,
Okay?
does this mean after 3.487 million times more than 50% can fail?
This means that the bearings life for 50% survival. You understand or no? Let me tell you. Then the life for the bearings to survive, okay, is 3,400,087 that's the number of cycle or revolution for 50% of the bearing. You understand that? Yeah. Okay. So if we go, yes.
Is it better to have a low standard deviation or high standard deviation?
Of course, it is always better to have low standard deviation in experiment. We think that when your experiment is repeatable, it means that whenever we repeat it, we always get almost close answers. Just like when I put the table over here. If you give me an experiment which will give me scattered value, I will tell you, come on, there's something going on here. But if you do experiment and then the standard deviation is too tiny, it means that, wow, your product is reliable. I mean, I can with high confidence say that the failure is after 2,000 hours. In here, in this one, the standard deviation is little. You get that?
دكتور
يعني يا شباب, if we measure the standard deviation for a student in the class and turns out to be around 5 or 6, it means in average, this is the markup for each grade, kind of. In average, okay, you are about 6 points far from the other student. In another word, you understand that? And when you become higher by 3 or 4 sigmas, that's why we say, wow, you are way higher than other student. That's the meaning of it. Okay.
دكتور
اتصور نويسر. Yes. لا شوي قصد. Yes.
always the median value will be correspond to reliability of 50%.
The median, yes. The median is 50%. Okay. Now, don't get this wrong. I want you to understand this very well. But this is way more important for what's coming next. So for now, I want you to understand, get familiar with the, numbers and values, and so it becomes second to nature, kind of. Now, look, this is very, very important. This is going to show you if you really understand what are you doing. So if you look at this, it is asking about the 10th percentile. Now, what happened if we find the dimensionless life measure X for 90%, for 10th percentile, then ايش قلنا احنا؟ The 10th percentile is for the failure. So what is the reliability?
90%.
Is 90. So I should go back to the equation, and in here I put 90%. Correct? Correct?
Yes.
Okay, good. Now, if I do this, what would I get? 1. And the book is saying as it should be. Why? Do you think this is, logical? Because the book is saying that.
Because rated life is 10 to the power of 6, so it's 1 L10.
Yes. The idea is that here, when you found X, by putting the reliability as 90%, you are actually calculating L10. So when you divide L10 by L10, you should get 1. You got that?
Yes.
Okay, good. So this is really good. Now here, the standard deviation, which has a gamma function as well. So you need to go to the table. And then when you find the standard deviation and the mean, you can divide them and get a measure of the variance. Okay? Now, what I want you to know is the following. What do we want? Is to relate the load, life, and reliability. Why? Because, as you will see, inshallah, we will start this next class. You don't want an airplane with 90% reliability. You go call the Saudi airline now, and instead of making a reservation, tell them, whoa. What is your R? Huh? What is it? They will never tell you probably 90. I don't think so. You can't just push people 30,000 feet with a 90% reliability. I don't think. So you want higher reliability. So what should you do? Now, here, you can play casual. Like you say, okay, if I want 99% reliability and the load I am applying is 1 kilonewton, if I go to the catalog, okay, the catalog will give me a value for 90%. 90. So what do I say? I say, how about if we use C10 equals to 3 kilonewton? Same size, same diameter. I can fit it on the shaft 3 times, good enough. Well, that's kind of the logic. The problem is this: we don't play when we design, we compute. You can expect, in general, that for a 90% reliability rating, you will get C10 equals to 1 kilonewton. And for 99%, you will get C equals maybe to 3 or 4, which means you are using much more stronger bearing in a place which only have lower value. And that's how you push your reliability. صح ولا لا يا شباب? That's what you can do. That's
Doctor,
one way. Yes.
like a factor of safety?
More or less, in a very shallow way. Why? Because look, ya shabab, before we end the class, and wish you a happy weekend. This graph showing us the logarithm of x, which is similar to life, right? It's L over L10. It's a dimensional life measure. And then here we have the log of the force, which is the force that acts on the bearing. And what do we get? We get, for 90% reliability, we get this curve. This curve is called the constant reliability curve. And what does it say? It says that if you want to run for X10, which is, let's say, 1 million, okay, you need to get C10 with a reliability of 90%, no more, no more. Okay, cool. Now, what about if you want different reliability? Now, I'm not going to talk about a higher reliability or lower. Of course, we know that people will always want higher reliability. But let's just forget about higher and lower. Let's just think about a desired reliability. Now, here, if you want a desired life, it will tell you that this is the desired force. But this force, if you go and pick it from the catalog, it will give you a 90%. So what should you do? You want to jump to this curve. And in the next class, because we ended our time, we'll show you how to move from this curve to this curve. Why? Look, we are going to use the catalog value, which only give us 90% reliability. But we will use a bearing which will give me 99 or 95 or something. You understand that? Thank you so much, Shabab. See you next class.
Thank you, Doctor. Have a nice weekend.